Good morning, all of you. I welcome you all in today's webinar. So today, Mr. Shubham Kumar will deliver his lecture on total synthesis of Strongylophorines 2 and 9. So before he start his lecture, I will like to introduce him to all of you. Mr. Shubham did his BSc from Garewal University, Uttarakhand, and then he did his Masters in Chemistry from IIT Dhanbad, and now currently he is a student in Professor Dethe's lab in IIT Kanpur. So over to you, Shubham. Start your lecture.
Good morning, all of you. Thank you, Tim, for your kind introduction. So, today we are going to present the webinar on the total synthesis of the Strongylophorines 2 and 9. So, actually, this webinar we have already discussed in the first section, but there are several issues was there, and our so many participants also requesting to proceed this lecture again. So, here we are again to proceed this lecture. So there are learning outcome of this lecture is that first thing we have to discuss here the basic definition of the total synthesis, because we have in this group there are several students from the BSc as well as the MSc background, so they don't know about the what is the total synthesis, what is the basic term in the organic synthesis. So we will cover a little bit all the topic here. So basic definition of total synthesis, then we come to the retrosynthesis analysis and protection of ketone by the ethylene glycol and reduction of conjugated ketone by 1,3-dipropane-diol. So this is the thing we have to discuss here. And after that, we will move to the comparison between the thermodynamic and kinetic favorable formation of enolate ion and intramolecular aldol condensation and Robinson annihilation reaction. This is very much basic from the BSc time, and also when we come to the contact to the organic chemistry like in class 12, so we met this reaction like aldol condensation is very much famous for all of the student. Then we will move to the oxidation of PDC, selenium dioxide and hydroboration oxidation reaction and IBX. There are some oxidizing reagent which we cover in this particular paper. Then this the novel reaction like carbon-carbon bond formation by the Wittig. So Wittig olefinogen, one of the and got Nobel Prize in I guess 1961 for this outstanding research. Then we come to the microdistant. So here we can discuss about the radioselectivity of the molecule, how a nucleophile attack to 1, 2 and 1, 4 selectively. So we will discuss here the radioselectivity between the 1, 2 and 1, 4 addition. Then major feature of the this webinar is the sp3ch activation evident by the PIDA mediated 1,3-diaxial substituent, which is known as the Soares photocatalysis condition. So this is the major thing which we will come to know about when we proceed the further one. So first thing is that introduction section. So the basic term is that there are the students who are from the BSc, MSc, and also PhD. So they want about our field because our research basically dedicated to the total synthesis of natural product. So here I have took the basic definition. What is the total synthesis? So total synthesis is a complete chemical synthesis of a complex molecule, often a natural product, from a simple commercially available starting material. So suppose that we are going for synthesis of any big molecule. So how can we make this molecule? So we have to find out a starting material which is available in our laboratory. So for this, we have to go some retrosynthesis analysis, which we will discuss in few further slide. So what is the target molecule? So for the total synthesis, we choose some target molecule like natural product, medicinal important active ingredient, and some organic compound for the theoretical interest we can do for the final product. So there are some history you might be know about this thing, because if you know this thing, then I guess you can dedicated to this subject like total synthesis. So first total synthesis was done by Waller in 19th century in 1821, and this is the urea which is found in our urines, and it is the solution of the inorganic compound like ammonium cyanide. Then later on, the groundbreaking research going on. And 1845, Colwell synthesized the acetic acid. And later on, there are several compound were synthesis. So I am not going to discuss the history of the molecule which is synthesis, but I took here very interesting molecule like glucose, and it was discovered by the Fisher in I guess 1890. And you can see here, and just wait a moment. Okay, so you can see here in glucose molecule, what is the beauty of this molecule and what is the complexity of this molecule is that we have 6 chiral centers there, 1, 2, 3, 4, 5, 6. So for this, uh, uh, our researcher feel very much difficulties to deal with to deal with the glucose moiety because it is very arduous to handle the all of the stereo center here. So nowadays, total synthesis is divided into the other part. One is the alkaloid based total synthesis, and second is the glycochemistry based total synthesis. So cis glucose based synthesis is known as the glycochemistry based total synthesis, and this is very arduous because it is not cakewalk for anyone to deal with all of this stereo center here. That is why this molecule is very much interesting, and Fisher synthesized this molecule in 1890. Where in which we don't have that kind of facility which nowadays present in our laboratory. So that is why he got second Nobel Prize in chemistry in 1902 after the J.B. Wondorf. So for this outstanding research, he got Nobel Prize in 1902. So now come to the our abstract section, which we have to discuss here. So total synthesis of the Strongylophorines 2 and 9, and as you know here, it is now very arduous to pronounce. So we can simply take abbreviation for STR2 and STR9. So here the abstract of the paper. So this paper is published in OL 2019, and it was published by the Dr. Dethe, which is our supervision in IIT Kanpur. So you can see this molecule here. So we are starting with two bicycles, the violin major ketone derivatives, and we further transform this compound into the tetracyclic lactone. And if we further treat this compound, we are getting the 6 hexacyclic compound here. So this is the beauty of this compound, and we can say that this is the also complexity of this compound. We are getting this 6 hexacyclic compound in which the variety of the ring is there. So we can say this is the carbocyclic ring. So 1, 2, and 3. This is the carbocyclic ring, and this is lactone here. One is the heterocyclic ring here, having the oxygen atom in the center position, and one is the aromatic ring. So we can say that with the diversity of the ring here, and aromatic, carbocyclic, heterocyclic, as well as the lactone ring we can see here. So this is the very much interesting molecule for the discuss. That's why I took this molecule so that I can elaborate this molecule with you. So whenever we can go for the total synthesis research, so we have to find out the starting material. So how can we get the starting material? So we have to thanks this research for the Professor E.J. Corey, who got Nobel Prize for the groundbreaking research in retrosynthesis analysis. So because we cannot directly make this molecule, so we have to find out the synthetic precursor which is available in our laboratory, as well as we can directly purchase from the chemical stores. Now come to the retrosynthesis analysis of the STR2 molecule. So here you can see that this molecule is known as the STR2, and we have to make this molecule. So first thing is that how can we get this one? So this is the Michael Addison simple chemistry is there. We took Michael Addison path, and we get two starting material here, starting precursor here. One is the aryl lithium, and second is the alpha beta unsaturated enone system. So we are getting tetracyclic enone and aryl lithium. When both are combined in presence of the copper salt, it can attack here, and after the cyclization, we get this compound. The first retrosynthesis and return we are getting here aryl lithium as well as tetracyclic enol. Now come to the how can we, because this is the simple product we can get in our laboratory and as well as the chemical store. But when come to this sections, we are not getting this one. So we have to further disconnect this one. So how can we disconnect this one? So we have a tetracyclic ketone here. And this tetracyclic ketone is get after the methylation followed by the allylic oxidation. So we have here this ketone moiety. So we can take Grignard, MeMGBr, Grignard, methyl Grignard, as well as the MeLi. So methyl lithium will attack here, get tertiary carbon, tertiary alcohol here, and after the dehydration, we can get alkene. This one. So we can get alkene, this alkene here. So question is that how can we get alkene exocycline more frequently as compared to endocycline? Because if we see here, 1 minute only. Because after the attack of the Grignard or methyl lithium, we are getting suppose that Me here, and this double bond is not double bond, it will be single bond. So we are here OH and Me. So we have choice to dehydrate is like one we can find double bond here or here or here, but we selectively make double bond here because this is the exocyclic double bond, and exocyclic double bond is more stable as compared to endocyclic because we are getting here exocyclic double bond is more stable because if we create endocyclic double bond, so it can create a steric hindrance and some repulsion between the molecule, and this molecule cannot be attained easily. So we get here selectively exocyclic double bond. Now so this exocyclic double bond after that treated with selenium dioxide and then further oxidation, we get this alcohol selectively here. Okay, now next thing is that how can we get this lactone here? So the retrosynthesis analysis we come to now there. This sp3ch activation takes place between this thing and this thing. After the sp3ch activation, we get this lactone majorly, and this axial alcohol is come from this ketone, which is the just result of the functional group interconversion. Then after that we come to this ketone. How can we get this ketone? So this ketone is the simple precursor of this one. So we get this alpha beta unsaturated ketone and transform into this one. And this alpha beta unsaturated ketone is simply get from the Robinson-Anderson type of reaction. So if we proceed Robinson-Anderson, so we get the one hexacycline here because Robinson-Anderson reaction, one of the important tool. After the pericyclic reaction, in which this reaction we get the like this. So we can get here 6-member ring, but after according to Robinson, we also get 6-member ring by without any heat and without any sink. So this is the simple retrosynthesis analysis we have discussed. So we can proceed our synthesis. So we can start our synthesis from here. Firstly, we can make this molecule, and how can we make this molecule? So we have to come this thing. So synthesis of the tricyclic alcohol. So we took very starting material, which is the derivative of the violent ketone, and this ketone is treated with the para-toluene sulfonic acid and ethylene glycol. So when we took this molecule and treated with the para-toluene sulfonic acid, so we have here two choices. One is this ketone, which is the isolated ketone, and second is the alpha beta unsaturated ketone. So choice of the reagent is that para-toluene sulfonic acid and ethylene glycol selectively protect this alcohol in presence of the this alpha beta unsaturated alcohol. Why? Because the electrophilic character of this isolated ketone is very much high as compared to this one. So we get protected ketone by the ethylene glycol, this one. Then second thing we have again here we took potassium tributoxide. This potassium tributoxide has two choice. It can abstract proton from this center or also from this center. So this is the selectivity between formation of inordinate ion from in kinetic and thermodynamic control. So if we took hydrogen from here, so we can get at extended conjugated manner inolate. So this is the by the help of the extended conjugation, we can get selectively thermodynamic favorable inolate here, and we can differentiate thermodynamic and kinetic favorability of any information of inhalation by the help of the choosing of base and reaction conditions. Suppose that if we substitute this potassium tributoxide with LDA, so LDA can make selectively kinetic favorable inolate because it is the very hindered base. So if we take LDA, it will abstract protons more efficiently from here as compared to this one. But we can control this reaction by taking inorganic base like potassium tributoxide. It will take proton from here and make a alpha beta unsaturated compound like this and make a extended conjugated based inert ion. Now this inert ion selectively attacked by this center. The question is that uh, it is very clear that attack will take place here and make this molecule. But thing is that what about the stereochemistry? So stereochemistry is majorly monitored by this axial methyl group because this is the this is the sp2 hybridized carbon. So it is the like a planar structure, and this methyl group is above the plane, and the whole thing are below the plane. So this angular methyl axial methyl group which monitor the reaction condition, and that's why this approaching electrophile will approach to the less hindered position, which is the alpha phase of this methyl atom, and it is attacked from the less hindered position and get this stereochemistry. So next thing is that how can we reduce this double bond? Our next target is that reduction of double bond by reduction of the double bond into this one. So we have several reagents for the reduction of reduction of double bond. The first thing in our laboratory, our site took H2PDC, which is very basic, and we read from the class 12. H2PDC is the hydrogenating reagent which can reduce this isolated double bond into the simple saturated alkene. But problem is that when we talk about the stereoselectivity of this reaction, so we get after the attack of the H2PDC, this reagent will selectively reduce to cis alkene as compared to trans alkene in 9:1. So we were very disappointed about the stereoselectivity of this reaction. So we took this strategy having MnDPM3 and PS phenylsilane. So this reagent is selectively reduce this double bond from the bottom side. If you know about this thing, I will give you some reference paper which is published in JAX, and it has a detailed mechanism and some substandard example which Saravani and group published this paper and published in JAX 2000, I guess 2006, and I will give you this paper to you in WhatsApp group. So this reagent selectively reduced the double bond from the bottom side. Now come to the this section. How can we reduce this double bond? So we can take here 1,3-propane thiol in presence of DF3OTF. So first thing is that when we take 1,3-propane dithiol, so it will what we can say that it can protected this one make a this 6-member thiol link. And if we take sodium and liquid ammonia, this sodium liquid ammonia desulfurize this thing and make simple we can selectively reduce this thing, because if we have suppose that you have made this reaction like Wolff-Kissner reduction and Clemens reduction. So in BSc class, in class 12, we read about this both reaction, Wolff-Kissner and Clemens reduction. But advantage of this reaction is only takes place when we have saturated ketone. Suppose that if we proceed our reaction here by Wolff-Kissner and Clemens, it will selectively reduce this ketone because this is the isolated ketone. But when we talk about the alpha beta unsaturated ketone, the alpha beta unsaturated ketone is not reduced by the Wolff-Kissner and Clemens reduction. So we have to choose other strategy with 1,3-propane dithiol in BF3OET, and this firstly make dithione compound like this, and after take of the liquid ammonia, this reduce this one. A second is that this alcohol, this ketone also reduced into alcohol, And furthest, this alcohol is protected by PBSCl and DMF. This is very this is a three-step reaction, and overall yield of the reaction is 70%. Now come to the hydroboration part. So hydroboration oxidation, one of the important tool for the oxidation of the alkene. So we have to, if we want to oxidize any alkene, so we can use hydroborating reagent. So hydroboration oxidation takes place here, and we can get selectively uh, beta phase from the beta phase of the secondary alcohol. After this secondary alcohol treated with PDC, pyridium chlorochromate, so we can get this OS converted into the this ketone. The secondary alcohol, when treated with oxidizing agent, it will convert it into the ketone. Now we take again PPS3CH2, which is very common reaction known as the Wittig reaction. So this Wittig reaction, what happen here, is this Wittig reaction converted into this ketone into alkene. And after that, we took BS3SMA2 and NaOH. Same reagent we get to here, BS3SMA2 NaOH. So this reagent selectively oxidize again this alkene into this alcohol. Now we have DMSO based oxidation, which is known as the Swern oxidation, in which we took DMSO oxyl chloride in triethylamine and DCM solvent. A reaction is optimum till minus 78 to 30 degree. And in this case, this primary alcohol is oxidized into this aldehyde. Now we have again this condition, potassium tributoxide and amide. So this potassium tributoxide amide, I will take hydrogen from here, and here's the just methylation takes place. And after that, after the methylation, sodium borohydride reduce this aldehyde into this alcohol. And if we take, if we look the structure, 3D structure of this molecule, so we have to make a chair compound. If we make the chair compound of this one, so we can get this one. So
Hello,
we will
sir.
see here. Hello.
Sir, I want to know that if you protect if you protect this alpha beta unsaturated ketone with a 1,3-propane dithiol, then you deprotect this into alkane. Can we use Rene nickel instead of sodium liquid ammonia?
Yes, you can also use Rene nickel and nickel boride also there, and but you can use Rene nickel as well as the nickel boride. Boride is more preferable as compared to Rene nickel because it's the updated version of Rene nickel.
Okay, sir. Okay. Thank you, sir.
Okay, you can ask question freely, but when I complete my presentation, there's a complete we have complete discussion session. So
Okay, sir.
if we
Okay.
make 3D, okay, thank you. If we make 3D analysis of this molecule, so we can get here this tricyclic compound in which this Me is below side and this OH is above side. So this is the absolute confirmation of this one. Then we move to the other compound. Now we have lactonization as well as enone formation. So we took this compound which we have already synthesized last step and took this compound with the PHIOSC and this thing, because our ultimate target, I will show here, make this compound here. We have to make this compound from this one. So first our group took a hypothetical CH activation process. So we find that if we activate here, CH activation takes place here, so we can easily convert this alkyl halide to this electron process. So hypothetical CH activation takes place. So our group finds that we can easily form this electron here. So but when we proceed in the laboratory, so we have to think like how can think possible, because when we think any reaction in our mind and in our laboratory, this is a very different thing. So our target was to make this electron from this one. So we choose hypothetical CH activation, and after the hypothetical CH activation, it is very easy for us to make this electron. But now I come to how can it possible. So this is a storage photocatalysis condition in which simple reagent PHIOSC I to H new condition is takes place, and this condition introduce here this iodoaldehyde. So this iodoaldehyde, this is also oxidizing agent. It will oxidize this alcohol to aldehyde, and there is a simple after the radical mechanism we get here iodine here. And then we took here picnic oxidation, in which we took NaCl2, NaClO2, and NaH2PO4. This picnic oxidation oxidizes this aldehyde into corresponding carboxylic acid. Now we have TBF at 0 degrees centigrade and in THF solvent. So we selectively electronize this one. So what happened here? TBF has free F negative. This F negative abstract this hydrogen here, and after the abstraction of this hydrogen, this O negative can take here and make a electron here. So this is the new methodology having we took because we have eclectic choice of the bases, but we took TBF as a selectivity. So this is the hit and trial method. You can say that because every researcher thinks that we can we do this thing by this thing, because we have a TBS group also or TBS group also, but selectively we took TBF because there's a hit and trial method. Yeah, hit and trial method. We can say that this TBF can deprotect this one or this one. So we found that this TBF this did not deprotect this one. Then we took other hit and trial method, which is known as TMS or TF and CS2Cl2. Because if we are a good researcher, so we try new thing again and again. So first daring thing we have done here, our laboratory done here, we took TBF. Instead, we know that this T or TBS group can be deprotected here. But although we took this TBF and this OTF group remains unstained and make electronation here. Then again we proceed again the another reaction, which is TMS OTF and DCM in presence of DCM, and reaction condition is 0 to 30 degree. So this in this time this OTS group is removed deprotected into this OH. Now we have PDC, pyridium dichromate. We again took here. So what happened here? This secondary alcohol will convert it into ketone. Then again PPS3CH2Br and potassium tripodioxide. So this is the starting metal for the Wittig reaction. So this is the reagent for the Wittig reaction, and this Wittig reaction convert this alcohol which is formed here after the oxidation. So we are getting this ketone, and this ketone is converted into alkene by the Wittig olefination. Then we took here selenium dioxide, which is also an agent. So this what is the feature of this selenium dioxide? So selenium dioxide oxidized to allylic. So we have this allylic portion. So we are here to OH group, which can be oxidized into corresponding alcohol. Then we took IBX. IBX also a good oxidizing agent, which oxidized to this allylic alcohol into corresponding enol. So we get here tetracyclic enol compound here. This tetracyclic compound is further. Okay, so our next strategy is formation of lactonization as well as the enol formation. So lactonization takes place here. After the lactonization, we get enol here. So this step takes place. Now next thing we have total synthesis of STR9 and STR2. So this is the last and final step of the reaction. So we have enol, which we synthesized last step. Then we took this starting material in copper mediated. So what we have here, we have a aryl bromide. This aryl bromide treated with butyl lithium. So this is the halogen metal exchange reaction, and halogen metal exchange reaction create this bromine to exchange into lithium atom. So this lithium metal and this complete reaction is known as the halogen metal exchange reaction. And halogen metal exchange reaction in presence of lithium is the very hard nucleophile, and this hard nucleophile is choice to attack here, not here. So we have to control the radioselectivity. So to control radioselectivity, we can efficiently use copper salt here. This copper salt make this lithium atoms as a soft nucleophile. Then it has a choice for the mica addition. So in the learning outcome, I had discussed that we can also talk about the how can we control the ratio selectivity of a nucleophile, or how can we say that it can go by the 1,2 and 1,4 position. So whenever any hard reagent like a grignard or butyl lithium and aryl lithium reaction is proceed under the copper salt. So this reagent becomes soft and it will efficiently attack from the 1,4 position. So what is the final product here? So we are getting this is the final product here. So this final product having the this phenyl atom, this aryl atom efficiently choose the uh, equatorial position, because if we talk about the cyclohexane system, so if we have the bulky substituent, so more due to gauge butane interaction, it will selectively choose the um, equatorial position. After that, what we have to do here, we took again here Wittig reaction. So in our research group, very much fascinated for I think Wittig. So we have seen a 3-time Wittig reaction proceed here. So this Wittig reaction converted this double bond into corresponding alkene. So this double bond change into corresponding alkene by the Wittig olefinación. Then we took I2PPS3, iodine triphenyl phosphine in presence of DCM. So what is the use of this thing? I will discuss you. But before that, I want to see the further reaction. So here we have H2PDC, which is the which is used for the hydrogenation of the alkene and unmasking of the OBN group. So if we have selectivity between hydrogenation of this alkene. Second thing is that unmasking of this OBN group. So if we take directly H2PDC, so it can unmasking this OBN group as well as it can also reduce this alkene to corresponding saturated hydrocarbon. So we have to prevent this thing because we want to this alkene here not want to reduce this alkene. So we have a synthetic problem. How can we protect this alkene when we add H2PDC, and we want our desired reaction is to deprotect this OBN group, but unwantedly we are getting to reduce this alkene group. So we can here. So we took I2PPS3. So triphenyl phosphine is in presence of iodine and DCM solvent. Here the isomerization takes place. So isomerization of alkene takes place from exocyclic alkene is converted into the endocyclic alkene. Now you can see that this alkene is tetrasubstituted 1, 2, 3, 4 to make a very hindered alkene. So as H2PDC. So H2PDC cannot approach to this center and this alkene is rigid for the hydrogenation. So we can took now directly H2PDC. Now H2PDC can deprotect this OBN group and our alkene remains unchanged during this process. Then we took BF3OAT, which can with this BF3OAT cyclize this weekend STR9. So now that we can get STR9, this STR9 now we have to deprotect this OBN group. So we can choose here triphenylborane in presence of ethylsilane, hexane, and 30 degrees temperature. Thus, when we proceed this action for 1 hour, we can get 83% yield, and we can get here STR2 as a selectively our final molecule. So this is the complete synthesis of total synthesis of STR9 and STR2. And when I go through this paper, so I was very fascinated that how a researcher can give to their friend. So I have found that our sir, Dr. Dethe, dedicated to this paper, Vinod Kumar Singh, which is the senior faculty of IIT Kanpur and one of the famous organic chemists in all over the world. So our sir dedicated this paper to Dr. Vinod Kumar Singh. So this is the motivation for my all best friend and who are doing research in organic chemistry and other field of the chemistry. So I hope in upcoming birthday you can also give me like this kind of the birthday gift, and I will be very happy. And same thing I want to do for you. So this is the very good motivation for all of us. So do like this. So thank you for listening, all of you. Now The special thanks I want to say here. So my lab mate Nitin and Chavi, Sweta, and Saif and Vishal Pandey for their continuous help and support to organize this kind of outstanding session during this COVID pandemic. Because now we all are at home, so we have to do some kind of thing so that we can interact with our senior, junior, as well as the people who are totally interested for the research. Because that we are at home, so we have to do nothing, but we can just attend our 1 hour and we can see how the people are doing research and what kind of research actually doing by each group. So that is why we initiated this thing, and I am very thankful to you that there are so many participants are adding day by day in our group and they are very much interested. So I hope in future we will do some kind of thing also, and I requested you that you all are the audience also and you all are the speakers. So please, if anybody has anybody want to do anything, so please let me know. We will organize this kind of seminar for you and you will be the speaker for us. Thank you so much.
Thank you, Shubham. I will definitely dedicate my first paper to you. Okay, now.
Thank you, Nitin.
Okay, the lecture is now open for discussion. If anyone have any question, please ask.
Shubham, I have a question.
Okay, Vishal, you can ask.
Shubham. I have a question in yes, in synthesis of tricycle, 6 number slide.
Okay.
Yes. So after using what 1,3-propane dithiol BF3OE2, we will get this one. Dithiol will attach at the position of ketone. So when we proceed again, so we what we do, we deprotect our diol ring. So generally we know that we are using acid for deprotecting our diol ring. So what you have done with it? So how you proceed next? We are not using.
Actually, we have acid here, BF3OET. This is also acidic condition here. BF3, this is Lewis acid mediated reaction, and this reaction is not one step. This is a 3-step reaction. In which first thing is this thing. This is all of the reaction mixture. So we proceed this reaction in acidic medium also. So that is why this what we can say that this moiety also deprotect here.
Okay, so we will just move ahead with the D step. Then we will move to that second one, E1. So E have a liquid ammonia also there. No? Liquid ammonia and sodium also there.
Liquid ammonia and liquid ammonia.
So
this is the desulfurization agent.
It just deprotect the ion. Okay.
And this is the problem. I guess last session, everybody asked me about this thing. How you can say that selectively this double bond or I think this double bond is converted into this thing selectively. So if anybody has doubt these steps, I can give you. I can clear your doubt. This thing. How can this thing to proceed this one? This is a stereoselectivity problem. So last time many of you asked about this thing.
Actually, this step is clear
to everyone.
Yes, this step is clear, but the step number J number
Okay,
step, how stereoselectivity control here?
Okay. Now I can give you the idea about this thing. Okay. So I can take only this ring. We don't bother about this thing. We have to see this transdecalin system. Okay. So that. So we have a this is Me and this is H. And if we do Wittig reaction here, so we can get exocyclic double bond. So this exocyclic double bond is there, sorry, in there, and this is the CH2 atom here. Now we have to do hydroboration oxidation reaction. So we have this Me and this is the H here. So this Me criteria is a steric hindrance. So we have choice for the hydroborating agent to approach from the alpha phase. So this is the alpha phase. This thing BH2 here, and this attach here, this attach here. Then we can get here selectively this is the Me and this is H and this is also H and this is the OH. Now question is that after the attack of the PDC, so this OH is converted into the this thing aldehyde. Now we have hydrogen here. So again we have base. This base can attack here and go like this and this. So again we have a trans-decalene here. And H here. So again we are getting here sp2 hybridized carbon like this. So this is the distereoselective reaction. So we have two phases here to attack of the upcoming electrophile. But here Me is again bulky group here, axial position. So it will not allow for electrophile to approach from this side. We have a small hydrogen atom here. So selectively we have Me. This is the key step to determine the axial alcohol formation. So this come back and selectively it will attack from the Me side like this, and we can get our final product. This thing. Having, and now we can say, so this is the completely planar form. So nucleophile either can approach from the above side or below side. But thing is that this axial methyl group create steric hindrance here for the upcoming electrophile. So this Me group selectively come from the below side. Now we have this alcohol, aldehyde. This aldehyde when treated with sodium borohydride, so we can get selectively OH from above side. So everybody clear this thing?
Yes, clear.
And one more thing here, also I want to discuss this thing clear to you. So if we talk about this ring, this one, so this is basically called 1,9-octalene system. So 1,9-octalenes, as we are all the trimester strength, so we have to draw chair form for this. So this is the basically octalene is found like this. We have axial methyl atom here. So now it is clear to everybody. So if we proceed our hydroborating reagent from this side, so this is the steric hindrance created by this axial methyl atom. So we have this phase for open to attack. This is called 1,9-octalene system, and this is called quasi-transform. It is not like trans, but we can treat as a quasi-transform. The second form will form quasi-cis, but I am not going to quasi-cis form. So this is hydrogen reagent takes place. So we can proceed hydrogen here and bromine here. So we can BH2 here. After the attack of the NOBH4, so we can get Me and trans-decalene, and we have here OH. And after the attack by the PDC, this chiral OH is transferred into a chiral thing, this thing. So we can proceed a distereoselective reaction. So I think now it is clear for everyone to check the stereoselectivity of the reaction. So whenever we have this kind of thing, we cannot directly proceed. What is the final outcome? So draw always chair form to predict the absolute stereochemistry, because until unless we don't know about the chair form, how actually the molecule looks like, we cannot predict which phase is more hindered, which is phase is available for the attack. So it is the better suggestion to all of you. So whenever you go for the cyclohexane reaction, please proceed the chair form. Now, any question?
Hello, sir.
Yes, Shruti.
So can you explain B step once again?
Which B step? This thing. This one.
PHSIH3. Yes, sir.
Okay. So actually, this step is very much important, because when we do hydrogenation, we have two choice. One is the we can proceed simple the H2PTC, Adam catalyst, H2PTC, and Lindler catalyst. There are so many reagents which is the heterogeneous catalysis based reaction. And second, those catalytic reactions are proceeded for formation of the cis decalene. But when we second method is that how can we get trans compound, so we can treat with this liquid ammonia, sodium liquid, like a Butz reduction. So Butz reduction can proceed from the transformation of inolate. So there is a sometimes it not give the 100% diester selectivity. So we have one more methodology here. I will give you paper, complete literature for this one. This is called HAT, which is known as the hydrogen atom transfer reaction. So hydrogen atom transfer reaction generally takes place by the radical mechanism. Okay, so what happened there? We can form here radical. So we have choice of radical, either we can form here or here. So you know the stability of radical can be explained by the hyperconjugation and what can the resonance and inductive effect. So this is the tertiary radical ion form here, and this tertiary radical ion is very much stable as compared to secondary. The first thing is that formation of radical ion. Now we have free H atom here for select. Now this H atom can selectively attack from the beta above beta phase or alpha phase. So we know that the transdecal is more stable as compared to cisdecal. Likewise, you can understand like this. Suppose that we have a carbocation, this thing. The carbocation is a planar structure. The nucleophile is choice, either it can attack from here, or it can attack from here. So there are two possibilities for the approaching nucleophile to attack the center. So we can selectively this that where the steric hindrances come, where we can find the major product, where we can find the product which has the low steric hindrance, we can go for this product. So when we form here a radical ion, this we have the hydrogen atom here. This hydrogen atom approach from either above, either below. If you know the gauge-Bettan interaction of the cis-decalene as compared to trans-decalene. So cis-decalene is less stable as compared to trans-decalene. So that is why we can get here selectively trans-decalene. So I will give you a paper published in JAX, which is very important. You can find out the heterogeneous hydrogenation based catalysts like H2PTC, Adam, Pullman, this kind of reagent, where you can get a trans-alkene. So you can get the what we can say that sodium liquid ammonia. But this is the new method, the hydrogen atom transfer mechanism. So this is very important, and this mechanism is formed by the radical. So firstly, you have to generate the stable radical which can form here. Then approaching nucleophile hydrogen can be transferred from either from the cis-decalene or trans-decalene. But you know what is who is the stable? Trans-decalene more stable. That is why we can get selectively this compound. Any question?
Okay, Shubham. Yes, Shubham, I have a question. Where you use deprotecting reagent TF, TMS, or TF. So I want to know that. See what was the driving force? Why they think of these reagents? So they will do some kind of a mechanism type of thing, or they just do hit and trial and they will.
Okay, listen. So first thing what happened in Vishal here, we have last time the question that why this TBF lactonation takes place, but this thing not happen here. This is not deprotecting here. So thing is that if we have secondary TBS group, it is very steric crowding. Okay, so steric crowding is there, a secondary TBS is there. So when we see any, when suppose that we can go in a book, we see a TBF, so we can think that this TBF will deprotect this, TBF deprotect this or TBS group. But it is not like this. It is totally depend on the reaction condition. So when you proceed reaction at the 0 degree centigrade, so this or TBS group is not deprotected by the TBF. It required minimum room temperature like a 25 to 30 degree, and 25 to 30 degree temperature should be there, and you have to reflux the reaction. So by refluxing you can deprotect this thing. But if you proceed the reaction at the 0 degree cold water like ice, cold ice, you want to deprotect this or TBS group. This is not deprotected by this condition. You have to maintain reaction condition like your temperature should be 25 to 30 degree, and you have to reflex the reactions for the complete deprotection of this thing.
Okay.
Now,
So no, I want to discuss about T1.
Okay, this one.
D.
So this,
Yes.
so TMS or TPF, what happened here? When TMS or TPF take place, so this is the one thing is here move TBS or TF. So when we react TMS or TF reaction with this thing, so we so reduce there's the elimination of this thing TBS or TF, and then there's the silyllation takes place or TS or TMS takes place, and this or TMS when do the strong acidic condition. So after the adding of the this reaction quenched by like BF3. After quenching with BF3, we can get here alcohol. So TBS group is removed like TBS or TF and make here silylating or TMS group. And when we quench this reaction by the BF3 at 0 to 30 degrees centigrade, so we can selectively reduce this thing into OH. This is the general methodology for the.
Okay, you don't put any step. This is not in the step of retrosynthesis. Means that if we are using something else, so it's another step. One step added here. Like that, you have written there now over 3 steps that reaction is going on.
So you can use, you can take your IS solution of this reagent when treated with this thing in DCM. So first thing what happen here, TBS or TF will remove, and here silyllation takes or TMS will takes place. And this OTMS group when treated quenched with trichloroborine and BF3. So this cleave the OTMS mode and make a OH. This is also new methodology, and this methodology also took our 2-3 paper where you can use TMS or TF to deprotect the OTBS group.
Okay.
Anything else, Bisal?
No, it's okay.
Okay.
Okay, Shubham, thank you for this
Hello.
beautiful lecture.
Hello.
Chef.
Yes, Shubham. In the step you are using after this means after TMS or TF, you are using PDC for the oxidation of secondary alcohol. So we can use other oxidizing agents like PCC or Jones reaction, IBX. Why we are not using these things? Why we are using PDC here? That is my question.
Look what happened in PCC and Jones are the highly oxidizing agent, and it is like a hygroscopic also. And same thing is like for PDC. And PDC reagent is like very effective for the oxidation of this alcohol into the what thing ketone. If we talk about the IBX, so IBX you can use in the laboratory, but it needs highly precaution for the set up the reaction. Means it requires high apparatus to proceed the reaction. But if you use PDC, so it's a less hygroscopic. So I think it is better for the oxidation for secondary alcohol. But we have several agents we can use also other one.
But I think there is one more factor that is affecting that the acidity of the reagent. If you use
Okay, and one
like
more thing. If you use PCC, so PCC and other reagent, John's reagent need acidic condition, and if we use acidic condition, so we can also affect this thing. This lactone
yes,
can also be
that one I'm asking.
deprotected. Okay,
Yeah.
thanks.
And please go to previous slide. In this step means deprotection of this thiol compound.
Hmm.
How you protected this thiol and this diol in one step? Can you please?
How can you? Okay, what you said?
How you deprotected means this thiol and this diol group in only one step, that is na liquid ammonia.
Okay. So what happened here? 1,3-propane dithiol in treated with BF3 agent. So firstly, thionization takes place here, and this thionization takes place. So we have some amount of acid is there. So this acid also can deprotect this alcohol and this ketal group. And if we take the sodium liquid ammonia, so uh, this sodium liquid ammonia. 1 minute, okay. This sodium liquid ammonia deprotect, desulfurize this thing. We are getting this one.
But one thing I have to say, if
Mm.
BF3OTF BF3O82 will deprotect this diol group, then then 1,3 propane dithiol protection will be there. That ketone group will be protected by this thiol group then, but it is not happening.
Mm.
Actually, Subham, if it is there, then the diol ring will remove out. So why it there? That's the question.
What you said? If PF3 diol.
No. My question is this: if we use
Mm-hmm.
BF3 O82, you are saying
Mm-hmm.
that the diol group will deprotect by using this BF3 boron what boron
Trifluoroborane.
ether trifluoroboran.
Mm-hmm.
Then this will be ketone, and
Mm-hmm.
1,3 propane dithiol protection will happen there also. I mean,
Mm-hmm.
okay, fine.
Okay. Firstly, we have to protect this thing. Then we use protect to this thing, and then can traditionally desulfurize this one. Also, we can use nickel borate, as I mentioned also already, but we use here sodium liquid ammonia.
Okay. Thank you.
Anything else? I think we get crossed the limit.
Subham,
Mm.
I think it's enough for today. Thank you, Subham, for this presentation.
Thanks, Nitin.
Okay, now
Thank
you
you
all
all.
can leave.